Hello, my name is Daniel Bonsa, and for today's podcast, we'll be discussing some of the effects that long term microgravity exposure has on bone growth. So let's begin by discussing some of the known negative effects seen in astronauts after long term microgravity exposure. These include the weakening of bones, which we'll be discussing in great detail throughout the entirety of this podcast, muscle atrophy, decreased blood volume and redistribution, cardiovascular deconditioning, immune dysfunction, vision problems, and ionizing radiation effects. So before we start discussing how microgravity affects bone growth and development, I think it'll be important for us to review some bone anatomy and physiology. Bones are usually categorized into four categories based on their shape. The first category are long bones, and these are the bones that you would think of almost immediately that look like dog bones. These include the femur, the tibia, and the fibula, and the metacarpals, which are the bones in your fingers. Next, we have our short bones, which include our foot's talus and our wrist's scaphoid. We also have our flat bones, which include our scapula and our skull. And finally, we have our irregular bones, and some examples are our pelvis and our vertebrae. To keep things simple, we'll look further into the anatomy of long bones. From this cross section here you can see that the exterior is made out of this hard cortical bone that surrounds a porous spongy bone. This spongy bone is made up of tiny intricate crossings called trabeculi where bone marrow could be found. This porous structure keeps bones both lightweight and sturdy. If we magnify a little bit closer, we'll find the basic structural unit of bone called an osteon. We'll go ahead and zoom into this picture here to get a better view. An osteon is a cylindrical weight-bearing structure that runs parallel to the bone's axis, and it kind of looks like tree rings in this picture here. Each one of these tubes are made up of layers of lamellae that are filled with collagen fibers which help your bones resist torsional strain. Surrounding each layer of lamellae are gaps of spaces called lacunae that house your mature osteocytes. And osteocytes are an important cell that help regulate your bones, and they monitor and maintain your bone matrix. And we'll talk about them a little bit in further detail. On to the next topic. We're going to go ahead and discuss how normal bone grows and maintains itself under normal conditions. This is called bone remodeling. And one thing to keep in mind is that bone is alive, it is growing, and changing all the time. And these are because of the osteocytes that we mentioned before that play an important role in regulating bone growth and maintenance. And they respond to stress and mechanical stimuli like the impact of your foot as it hits the ground while running, or conversely, the lack of mechanical stimuli that you would experience while in weightlessness. One of the cells that osteocytes regulate are called osteoblasts. These are your bone builders. They use cartilage as a framework and produce and deposit an organic collagenous protein matrix called osteoid. They also absorb minerals like calcium phosphate from the blood and deposit them within the matrix to make a crystalline structure along the collagen scaffolding. Many of these osteoblasts do become embedded within the matrix and then differentiate into osteocytes. From an early childhood to maturity, growth is stimulated by growth hormones that come from the pituitary gland that stimulate this bone formation. On the other hand, osteocytes also regulate osteoclasts, which are your bone breakers, or less scarily said, your bone reabsorbers. Bone serves as a reservoir for a whole bunch of minerals and other important molecules that are important for biological functions. And these osteoclasts liberate these minerals and molecules stored within the matrix, like calcium phosphate and growth factors. And they do this by creating an acidic environment between the underside of the cell and the surface of the bone that dissolves the mineral content. Then they'll release enzymes that break down the remaining collagenous bone matrix. Now, this fine balance between osteoblasts and osteoclasts was noted by Julius Wolff. He was a German anatomy professor that came up with Wolff's law that states that bone will adapt to the loads under which they are placed. An example of this is a professional weightlifter. Professional weightlifters are known to have increased bone density around their joints due to the increased activity that they present daily. On the other hand, people that are bedridden due to injuries or illnesses or due to old age, they'll be seen to have diminishing bone densities due to the lack of mechanical stimuli on their bones. So we'll go ahead and move on to the next topic, which has to do with bone physiology and regulation. We'll start off by talking about the regulation of osteoblasts, which is dependent on the Y and T signaling pathway. It plays a key role in the skeleton's ability to strengthen bone in response to mechanical stress and is involved in the disuse-induced bone loss, which we'll talk about a little bit later on. Uh, Activation stimulates osteoblastic activity, meaning that they'll differentiate precursor cells into mature osteoblasts, overall increasing bone formation. Sclerosin is a signaling molecule synthesized by osteocytes, which, if you remember, are the regulating cells of bone, and they are a potent inhibitor of bone formation. They bind to the membrane receptors on osteoblasts, inhibiting the Y and T signaling pathway, overall reducing osteoblastic activity. Osteocytes respond to mechanical stress by producing less sclerosin, increasing osteoblast-mediated bone formation. So if you take that into the context of this podcast, reduced mechanical stress via a microgravity environment will increase the expression of sclerosin, overall decreasing the osteoblast-mediated bone formation. So next, we'll go ahead and discuss the regulation of osteoclasts. So when blood calcium levels are low, the parathyroid gland releases parathyroid hormone, or PTH. PTH stimulates the production of rank ligand, which is produced by osteoblasts. Rank ligand binds to the receptors of precursor osteoclast cells and triggers the fusion of these precursor cells into a mature multinucleated osteoclast. Osteoprotogerin, or OPG, is also produced by osteoblasts. It serves as a functional antagonist, which prevents the interaction between rank and its receptors, overall reducing the amount of bone absorption. And there are various hormones and cytokines that balance the amount of rank ligand and OPG circulating in the bloodstream. Estrogen is one of these hormones, which increases the expression of OPG, which again reduces the amount of bone absorption. And then this final slide here is just a kind of a visual representation of what we just discussed. So if you want to take a minute and pause the video to really get a full understanding of the regulation, go ahead and do so, and I'll meet you afterward. So now we can move forward and actually start discussing what the effects of microgravity are on an astronaut's skeletal system. And some of the findings that have been made have been from astronauts being sent to and from the ISS and taking pre- and post-flight evaluations. Some of the findings that we've seen are that longer missions do correlate with greater bone loss. On average, astronauts will lose between 1 to 2% bone mineral density per month. And if you compare that to individuals here on Earth that are aged 50 or older, they lose around 0.5% bone mineral density per year. So there is a considerably higher acceleration of bone loss seen in astronauts in space as compared to more elderly people here on Earth that also experience bone loss. Another finding is that initially bone loss was seen in weight-bearing bones such as vertebrae and lower limbs, and then later seen in less weight-bearing bones. And this should sound a little bit familiar because we did kind of discuss this a little bit earlier on. It has to do with Wolff's Law. The difference in weight, mechanical stress seen in the lower limbs is a lot more drastic than that seen in the less weight-bearing bones in the upper limbs. So it would make sense that you would see bone loss there first before you would in the less weight-bearing bones. Some of the secondary effects seen are that astronauts have an increased risk of renal stone formation, which is the formation of kidney stones, due to the elevated calcium in their blood. And this is because of the increased osteoclast activity over the osteoblast activity. Another finding that we've seen is that there is variable susceptibility to bone loss, and this could be applicable when we start planning missions to long-term missions to Mars. We may be a little bit more selective in the crew that we choose, and choosing individuals that have a lower susceptibility to bone loss, because as you can see for the next finding, recovery for post-flight may take around 3 to 4 times longer than the flight duration. So quite a considerable consequence for long-term flight duration. So you would definitely want an individual that has a lower susceptibility to bone loss. So now we can move on to the final topic of the podcast, which has to do with the ongoing research into countermeasures to prevent bone loss. But I couldn't go any further without giving recognition to the Kelly twins and their contribution to this ongoing field of research. They've provided an excellent model to really compare and see what the effects of long-duration spaceflight has on not only our genetics, but on our physiology and other bodily functions. And they provided many new findings and probably will provide new findings for years to come. But on to the research into exercise. In a bed rest study, which simulates the effects of long-duration spaceflight, resistance training showed that it had a positive treatment effect and and it served as a useful countermeasure. It increased bone formation and suggested that resistance training is a countermeasure to disuse-induced bone loss, which we discussed earlier. In another study, resistance training plus aerobic exercises reduced bone mineral density loss, promoted bone formation, but had no effect on the rate of reabsorption. In 2008, the International Space Station received a new resistance exercise equipment, which is the ARED, which is, we can take a close-up of it right here. It allows you to do some squatting, deadlifting, and other exercises that are good for preventing bone loss. In a recent study that looked at 46 ISS crew members from the years 2000 to 2013, compared the different exercise programs from before 2008, before the ARED was installed, and after 2008 when the ARED was installed, and they found that the ARED did protect astronauts from severe bone mineral density loss. So, that's a very good thing for the astronauts, and more research is definitely still need to be done. And that is the end of my podcast on the effects of microgravity on bone growth. Obviously, this is a very prevalent topic nowadays as we begin our talks in preparation for long-duration space flights to both the moon and Mars. Obviously, much more research needs to be done on the subject before either of them can be done. Much more research on the recovery methods once they reach their destinations and how to maintain their bone integrity while they're at their destinations, and then for their flight back if that is the option. But thank you for listening to my podcast. Again, my name is Daniel, and have a great night.